Hey, everybody. It's Friday, January 22nd. And as you can see here in the aim today, we are picking right back up where we left off yesterday by talking about how we can use conservation of energy to solve problems when there's friction involved. So, yesterday, we began to talk about this after we finished the questions that were in that worksheet that was posted on Wednesday. And then we began to talk about conservation of energy and friction. And I eventually, after sketching out some concepts, went ahead and solved a problem that I kind of want to revisit a little bit, at least in terms of the concepts that were involved, because I approached the problem yesterday in kind of a less formal way than it would ordinarily be approached. And the reason why that problem was approached in a little bit less formal of a method, and by less formal, I just mean than the way we would traditionally do these things, using, equations that are more accurately labeled, so to speak, is to get across the concept that what we are saying about friction and how it is involved in conservation of energy problems is not that complicated. If you remember, this problem here involved a kid sliding in to second base and being slowed down by the force of friction. Of course, you could, based on the information given in the problem, calculate the force of friction, use that force of friction to calculate the kid's acceleration, use the acceleration along with the initial velocity to calculate how far he slides, but that's a lot of steps. And what we tried to show yesterday is that the definition of work, specifically that work is equal to the change in energy, according to the work energy theorem, is still applicable here to friction. And so what we ended up doing, as I showed in a bunch of separate steps, is I showed the change in kinetic energy as the work, and then went ahead and just used the regular old work equation to calculate the distance here. And while all of that is accurate, what we want to do here is sort of sketch out a more sort of formalized approach to it. And so what we're going to say here is that since friction is a force just like any other force, we can use the general form of the work equation to write a general equation for the work due to friction. Now, yesterday you might have seen that there was a little bit of weirdness with the signs here, that because specifically you have to deal with the force and the displacement and the angle, and it can get to be a little confusing. What we're going to do is we're going to just sort of simplify the process. We're going to write here first the symbol for the work due to friction. And generally, when we write work, we label it with a capital W. And so to denote here that this is the work due to friction, we're just going to put a little subscript F on there to label it as the work due to friction. And for the equation here, simply enough, we're just going to say here that the work due to friction is equal to the friction force times the displacement. And that's it. Now here specifically, the delta x here, which we traditionally note as displacement, is actually technically the path length, which really is a measurement of the distance. But we always label that as delta x. Frankly, I'm not really sure why we always do that, but that's generally how it's done. You could label it, though, as a d if you want. And so I'll actually write that here separately, just so we're all on the same page. So the force of friction times d. Either way, it's perfectly acceptable. And we'll go ahead and label here that the force of friction here is the F with the subscript F, force of friction. And since in all these problems, the energy will be changing because the object is going to be in motion, you can go ahead and label that with a K if you want. It doesn't really matter. It is the force of kinetic friction, though, and so we should be clear about that. And then we're going to say delta x slash d is the path length or distance. And that, of course, is going to be measured in meters. And then the unit here is going to be the joule. Now, we should be pretty clear in noting that since friction always removes energy from systems, the work done by friction will always be negative because it's removing energy from the system. However, how exactly you arrive at that can vary. It should be noted that the cosine of 180 degrees is -1. And the reason why the cosine of 180 degrees is relevant to us in this situation is because the force of friction is always going to be acting opposite of the displacement in these problems. And if you consider also that the force of friction is acting opposite the direction of the motion, then you get a bunch of negative signs which end up canceling each other out depending on what you're solving for. And so the key point here that we want to make is that when you're using this particular equation, you shouldn't go all that nuts about the signs. Because it should be noted, since friction always removes energy from systems, we can always consider it to be negative. And we can always just do that on the back end, too. It's important to realize. We could just write after we calculate the work due to friction, this is supposed to be negative because it's removing energy from the system, and sort of just acknowledge there that, yeah, we didn't go too nuts about the signs in our calculation, but we're acknowledging here that this thing is not gaining energy because of friction, it's losing it. And that's an important point. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So that's an equation for the work due to friction in terms of the friction force. Sometimes you're not given the friction force, though. Sometimes you're given just other information about the problems. And so I don't want anybody to lose sight of the big picture concepts because we are introducing this equation here. And so what I want to write down here is the work done to friction's most general form would just be an equation that looks like this. The work done by friction is equal to the difference in the final and the initial mechanical energy. So really, if we wanted to expand this out as much as possible, it's going to look a little insane, but we could write here, the work done by friction is going to be the final gravitational potential energy, kinetic energy, or elastic potential energy, and it could be all of those at the same time, depending on what the problem is, minus the initial kinds of mechanical energy, and it's going to be those same three again. Now, in almost every single problem you're ever going to see in this course, a lot of these 6 types of energy here, and by 6 types, I mean the 3 individual types, but the final and the initial version, a lot of these are going to end up being 0 for any particular problem. But it's important to realize this version of the equation, like we said, it is extremely generalized. This version of the equation will always make the sign work out to be negative for the work done by friction. So we'll say this version will always make the work done by friction negative, which we said it should be in order for the signs here, or the actual energies here and the signs to work out correctly. And so the most straightforward thing, or the clearest thing that we can say about this, is the equation you use for the work done by friction ultimately depends on the information that's given to you in the problem. And that's not a new idea in this course. The way you approach a problem depends on what they tell you about the situation in general. Now, before I ask you to pause this video here and write that down, which I do want you to do because we are going to be using this quite a bit, is sometimes you will see in various problems that they will write this equation that I wrote here in the box like this. And it basically, the only difference, and you'll just see that I'm writing the rest of this exactly the same, the only difference between what I've shown in the box and what I'm showing down here is that instead of writing W with the subscript F, they write W with the subscript NC, and you will see me do that from time to time on homework solutions just to remind you. They label this with the W with the subscript NC because they're saying that this is the work done by a non-conservative force. Because remember, the fact that friction is a non-conservative force means it's taking energy away from the system that can never be recovered. And so this is the work done by a non-conservative force. But notice it's the exact same thing. And so what we are saying here, to be perfectly clear, is that WNC really is the same thing as the work done by friction, because friction is a non-conservative force. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So let's take a look at a problem. This problem here is in the work energy packet. It's on page 6, number 47. It says a 16.0 kilogram child descends a slide 2.20 meters high, starting from rest, reaches the bottom with a speed of 1.25 meters per second. It says how much thermal energy due to friction was generated in the process. Wait a second. Thermal energy due to friction? What exactly is happening here would be a perfectly reasonable question for us to ask. And so that's what we're going to take a look at now. And so the first thing we want to say here is it's important to remember the basics. Friction always produces heat, and work always changes energy. Now, we did say earlier that sometimes you have to be very careful about distinguishing whether forces exerted between objects are acting within a system or separate and apart from a system, because that ultimately determines how you analyze the energies present in the system and so how they interact with each other in the problem. But the point here is friction is a type of force that will always do a very specific type of work. I want to go back to the very beginning and explain this. Let's say we have a ball sitting above the surface of the earth. The main thing that we were saying when we were talking about how you have to think carefully about the system is that if you don't consider the earth to be part of the system, then the force of gravity is external to the system. And if the force of gravity is external to the system, then it's doing work on the ball, increasing its energy. And that should make sense because the ball is sitting there at rest. Because the earth is not part of the system, there is no gravitational potential energy. So this thing is sitting there and it just has no energy at all. It's at rest. Then when gravity pulls on it, it accelerates it, gives it kinetic energy, and the object gains energy. The work increased the energy. The force of gravity would be in the direction of the displacement for an object in free fall, so it increases the energy. On the other hand, if we consider the earth to be part of the system, now the force of gravity is existing within that system. We should be very clear about this distinction, though. The fact that force of gravity is part of the system doesn't mean it's no longer doing work. It's still doing work. It's just not external work. It's a fine distinction, but it's an important one, because the force of gravity still definitely does work because it changes energy. It just doesn't change the amount of energy. In this kind of situation with a ball falling to the surface of the earth, it's not changing the amount of energy, but it's changing the type of energy from gravitational potential to kinetic energy. And so work, depending on exactly the situation, the system that is considered in the problem, et cetera, sometimes changes the amount of energy and sometimes changes the type of energy. And in a lot of cases, it could be both at the same time. The point that we're trying to make here is that the work that's done by friction will always turn mechanical energy, and that's going to be gravitational potential energy, elastic potential energy, or kinetic energy, into thermal energy or heat. Thermal energy is another word we use for heat. And if you remember from chemistry, we give thermal energy or heat the symbol Q, and that Q is uppercase. And of course, because heat or thermal energy is in fact energy, it's going to be measured in units of joules. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So we can also say, which is a very important note here, that the exact amount of mechanical energy lost is equal to the exact amount of work done by friction. That's true from the work energy theorem. The work is equal to the change in energy. So whatever amount of mechanical energy is lost, that's the exact amount of work done by friction. And the key detail here, which is probably the only part of this that's actually new information, is that the work that's done by friction is equal to the exact amount of heat or thermal energy generated. This is a very important note. It's a very important thing to think about because it gives us another way of thinking about solving a problem. The reason why it gives us another way of thinking about solving a problem is because when you write a conservation of energy statement, the initial energy equals the final energy, that's an equation for energies. You can't really put work in an equation for energy because work isn't energy, it's the change in energy. As you'll see, this will work out to be very similar, but sometimes it's like a nice little shortcut when they ask you for the work done by friction to just approach it as a regular straight up conservation of energy problem, where you say the initial energy is equal to the final energy, and then you just find the work done by friction by finding the heat. And hopefully, we'll be able to go through this problem and show that they are exactly the same thing, just sort of talked about it a different way. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So I'm sure, or at least pretty sure, at this point, a lot of this may seem a little confusing to you. And that's perfectly reasonable. It's a lot easier to explain, or at least it's a lot easier for me to explain, in the context of a problem. And so that's really what I want to do here. And so what we're going to do is we're just going to look at this problem from the work energy packet, page 6, number 47. Again, it says a 16.0 kilogram child descends a slide 2.20 meters high and, starting from rest, reaches the bottom with a speed of 1.25 meters per second. They're asking us how much thermal energy due to friction was generated in this process. Now, I think a smart thing to think about here when you start these problems is the answer to the following question, which is, how do we know there's any thermal energy generated due to friction at all? I usually don't ask you to do this, but I actually want you to take a minute to pause this video here and just think about that. How do we know there's thermal energy generated in this process at all? Take a second to pause this video here and think about that. When you hit play, we'll talk about the answer. This is something I want you to actively do as you're going through these problems on the homework because I think it's a smart idea. A lot of times I do this for my own benefit too, specifically because it takes like 2 seconds with your calculator in front of you. You should be, if you've been watching all these videos, fairly familiar by now that when you take gravitational potential energy and you convert it to kinetic energy, you get mg delta y equals 1/2 mv squared. And when you solve that for v, the final velocity, you end up getting this equation, 2g delta y, which we said is really similar to the result that you would get from the time-independent kinematic equation if the object started from rest. And so the final velocity equation is always going to be 2g delta y when it's simply a straight up conversion from gravitational potential energy to kinetic energy. And so what I like to do just for my own edification when I'm starting these problems, because this could be a multiple choice question where one of the answers is 0, and we can very easily check to make sure that the answer is 0 or not, because all you have to do to make sure the answer isn't 0 is just calculate what would the speed be if there was no friction. Now, you don't ever have to write this down if the question is like this, but if you just use the height, 2.20 meters, and you multiply it by 2 times 9.81, that number, if you take the square root appropriately, tells you what the speed of the object would be if there was no friction. And if you calculate the speed of the object when there was no friction, 2 times g times delta y, and you take the square root, the answer you get is 6.6 meters per second. So we know automatically by doing that calculation that there is friction. And so friction does generate thermal energy, because if there was no friction, the kid would reach the bottom of the slide with a speed of 6.6. And they only reach the bottom of the slide with the speed of 1.25 meters per second. So we know that friction is doing pretty significant work here, pulling out that energy that the object had present in the beginning. Now, as I mentioned before, you have a lot of options for how to solve this problem. But I think it's important to realize, especially when they ask you for how much thermal energy, when they say it like this, you should definitely be thinking about this in terms of just a straight up conservation of energy problem. And so the question here is, how's that going to look? And it's going to look like this. So obviously the first thing we do when we solve a problem is we write down the known. So they tell us here this kid's got a mass of 16.0 kilograms. They say this slide is 2.20 meters tall. They tell us the final velocity here is 1.25 meters per second. It should be clear to everybody by now that we're going to need G for this problem. And we are looking for the heat, which we are going to label as Q, obviously, because that's the symbol for heat, but also with a subscript F, because if you think about this in terms of a regular straight up conservation of energy problem, you have initial energies and you have final energies. And the heat is always going to be on the final side of the equation, because there is no heat before the kid starts sliding. The heat is only generated from the frictional contact that the kid makes with the slide as they're sliding down the slide. So in the initial state, when the kid is just sitting there at rest on the top of the slide with the gravitational potential energy, there is no heat. The heat only shows up throughout the process and then ultimately is there at the end. And so that's the key to the problem. Thinking about this as a straight up conservation of energy problem here, you have the initial gravitational potential energy is equal to whatever amount of kinetic energy is due to that tiny little speed there at the bottom, plus the amount of heat that is generated. And so the advantage of thinking about work due to friction as heat and vice versa is that now that we are talking about an energy, which is just an energy, heat is just an energy, and not work, which is a change in energy, which means you can't really kind of use a conservation of energy approach there by just saying initial energy equals final energy. The advantage here is that you get to use this approach, initial energy equals final energy, and just go from there. So notice, if we have the final heat, or we solve this for the final heat, we get gravitational potential energy minus the kinetic energy. And that's it. Notice, effectively what this is saying is the heat is just whatever the missing energy is. Let's say this object, and this is not true according to the numbers, but let's just say this object started off with 100 joules of gravitational potential energy, and then it ended with 1 joule of kinetic energy. How much is missing? 99. That's what the heat would be. Whatever amount is missing is turned into heat. And so that's exactly what this equation shows. The object starts off with a certain amount of gravitational potential energy. Some amount ends up as kinetic energy, but it's less. So to find out how much is missing, you just subtract those things. And once we do that, we approach this thing as just a regular old conservation of energy problem. mg delta y minus 1/2 mv squared. Notice we're subbing in our energy equations here like we usually do. Now, because there's heat present, the mass doesn't cancel. But as we know, the mass is going to have no effect on the final speed here. And so we just continue on plugging in the numbers. You could factor out the mass if you want to. You don't have to. It's up to you. I'm actually not going to do that here just so I can wrap this thing up here. So I have 16.0 kilograms times 9.8 meters per second squared times my height, 2.20 meters. And then I'm going to subtract my kinetic energy, 1/2 of the mass, which is 16.0 kilograms, times my final velocity squared, 1.25 meters per second, whole thing squared. And when you do that math, plugging in all those numbers here, you get 16 times 9.8 times 2.2, and then you subtract your 1/2 mv squared, and that's going to give you 332.46 joules, or to three significant figures, 332 joules. And that's it. We approach this problem as a straight up conservation of energy problem to find the heat. Take a second to pause this video here and write that down if you didn't get a chance to already. And when you hit play, we'll move on. So before we move on to the last problem here, I just want to demonstrate one more quick point about this approach. What we said before was that, and I'm going to go back to the slide here, the exact amount of mechanical energy lost is equal to the exact amount of work done by friction, which is equal to the exact amount of heat or thermal energy generated. Let's pretend for a brief moment that instead of this question, we asked a question that was exactly the same up to the point where this line is, and below the line it said how much work is done by friction. Well, as we mentioned a bunch of slides ago, the work that's done by friction in a problem like this, where they're just giving us the type of energies, is just the difference between the final and the initial energy. And so notice here, if you were to do that, you would say, okay, well, the work that's done by friction is equal to the final energy minus the initial energy. So what's the final energy? Well, the final energy is the kinetic energy that this kid has at the bottom of the slide. And the initial energy is the gravitational potential energy that this kid has at the top of the slide. And that's it. Notice that equation says K final minus gravitational potential initial. Final kinetic minus initial gravitational potential. And this equation for the heat was initial gravitational potential minus final kinetic. I hope everybody realizes, and let's go back to this situation that we had before, just for the sake of ease and thinking about it, where the numbers were 100, 10, and 90, that if you take 100 minus 10, or 10 minus 100, you get the same answer. It's 90. The only difference is that when we do 10 minus 100, as this equation is telling us to do, the answer comes out negative. And that ultimately is the distinction between the way that we approach these things mathematically. When we are solving these problems, you can choose to do the approach using the heat in a generalized conservation of energy technique. And then if they ask you for the work that's done by friction, you just take the negative of the heat. Conversely, if they ask you for the heat, you can also just find the work done by friction. It's going to come out as a negative number because you're taking a final energy, which is smaller, and subtracting an initial energy, which is bigger. And so that by default is going to come out as negative. And then just negate it to find the heat. Now, obviously, negating a negative is going to make it positive, but you get the idea. The whole point is heat is an energy like any other type of energy. And because there's changes in energy involved in the problem, because friction is doing work, the work done by friction is just like any other work. And so the work energy theorem applies. Take a second to pause this video here and write that down. And when you hit play, we'll summarize what we've said thus far. Okay, now very quickly before we move on to the last problem for the day, I just want to very briefly summarize all of the equations that you could ever possibly use when you are solving conservation of energy problems when friction is involved. The first equation is that work due to friction equation that we talked about at the very beginning, first here, with the friction force and the distance. This kind of equation is used most generally for problems that are referred to as stopping distance problems, where you are asked to find out how long it's going to take an object to come to a stop, like that kid sliding into second base, or a lot of times they do that with a car jamming on the brakes on the road. Either way, it's the same idea. You take the friction force, you multiply it by the distance to find the work. And so if you already know the work, you divide by the friction force to find the distance. The other equation here is by using the work due to friction equals the final energy, specifically the final mechanical energy, minus the initial mechanical energy. And we can expand that out, but we already wrote that down before, so you can just refer back to that. And the other equation is to say the initial mechanical energy is equal to the final mechanical energy plus the heat, where the heat is equal to the negative of the work done by friction. Depending on exactly how the problem is set up, you can use any of these equations, obviously depending on what's given, but this list is pretty definitive. Take a second to pause this video here and write that down. And when you hit play, we'll take a look at one last problem here before we go. Okay, so this problem with the kid on the playground slide is a little too easy. Notice this is like a level 1 problem. I'd like to take a look at a level 3 problem before we go. This problem here says an inclined plane fixed at an angle of 30.0 degrees is 6.40 meters long. A book, which has a kinetic coefficient of friction of 0.20, is placed at the top and immediately begins to slide. The problem then says, using energy considerations, how fast will the book be traveling at the bottom of the ramp? What I would like you to do here is I would like you to make a list of knowns, try to write the general conservation of energy statement, initial energy equals final energy, and try to expand it out as best you see fit. You don't actually have to plug in the numbers just yet, but I want you to see how it's going to end up working. What is the most sensible way to go ahead and solve the problem? And then we will take a look. So pause this video here, make your list of knowns, try to take your conservation of energy statement as far as you can before actually solving for anything. And when you hit play, we'll go over it. So notice here, they've told me a couple things. They've told me here that the angle is 30 degrees to 3 sig figs. They've told me that the length of the ramp, which we can call delta x or d, is 6.40 meters, also to 3 sig figs. So everything I'm going to do here is going to be to 3 sig figs then. They've told me the coefficient of kinetic friction for this book is 0.20. Those are actually usually only given to 2 digits. And obviously here, or it should be obvious, I'm going to need G, 9.8 meters per second squared. And they're asking me for the final speed of the book. The most general form of a conservation of energy equation that we could have is that the initial gravitational potential energy, which the object possesses at the top of the ramp, is going to be equal to the final kinetic energy plus the heat. Now, there are other ways that you can solve these problems, but I think it's probably a smart idea to always consider it just from a general conservation of energy perspective, because then you don't need to go nuts about thinking of different ways to solve it. Like if it's this kind of way, then I'm going to solve it this way. And if it's written like that, then I'm going to solve it like that. This approach will always work. And so now we have to expand this out a little bit. The first thing that we can do here is we can say, well, the gravitational potential energy for sure is going to be mg delta y. And they didn't tell us the height. We actually have to find that in this problem. Whether you realize that or not, we can find it, but we have to do that. But we'll save that for a couple minutes. Then obviously the final kinetic energy here is just going to be 1/2 mv final squared. And that's what we're solving for. Good. And the heat is equal to the negative of the work due to friction. It's just the absolute value, so to speak, of the work due to friction. And the work due to friction, remember, is the friction force times the distance. So that's what we have here. Now we got to expand this out a little bit, and we can do that. We have mg delta y is equal to 1/2 mv final squared plus the coefficient times the normal force times the distance. This is a part where you're going to need to be really, really, really careful, because a couple times we've seen this before. We've written coefficient times m times g times d. You're not doing that here. It's on a ramp. The normal force is not equal to the weight. The normal force is equal to FGY, the vertical component of the weight. And so now we can expand this out. See, I told you this one was tricky. It's a level 3 problem. mg delta y equals 1/2 mv final squared plus mu times mg cosine theta times d. Okay, now one of the first things I hoped you realized was that they didn't give you the mass. And if they don't give you the mass, it means you don't need it. Luckily, there's a mass in every term, so we can just go ahead and get rid of that. But now, we're ready to go. All you have to do to solve this for the final speed here is move over that term by subtracting mu g cosine theta d, and then multiplying that whole thing by 2 and taking the square root. Let's just show the subtraction part first. We'll just like sort of fill it in backwards. So we have g delta y, and then we're going to subtract that mu k g. I'll write the d first, times cosine theta, just because it looks a little weird, cosine theta d. And then notice here, that would be equal to 1/2 v final squared. So I got to take that whole thing and multiply it by 2 to get rid of the half. Now that would just be equal to v final squared. And so I got to take the square root. And that's my equation for v final. As we mentioned, we're actually going to end up doing that calculation on the next slide, because as we mentioned, we don't have everything in that equation. We have the angle, we have the distance or the length of the ramp, we have the coefficient of friction. Obviously, we know g, but we don't know the height of the ramp. Now, luckily, the numbers in this problem work out quite easily, but it's important to realize for this ramp, they told us that the angle is 30 degrees, and they told us this measurement, the length of the ramp. We need the height. The angle being 30 degrees is clutch, because they make it nice and easy for us to solve. The sine of the angle is equal to the opposite side divided by the hypotenuse. It's a ratio. The sine of 30 is 1/2, so that's pretty cool, because the opposite side is equal to h times the sine of the angle. H here is the distance, or the length of the ramp. The sine of the angle is a piece of cake here, and then the opposite side, notice, is delta y. So delta y here is just the length of the ramp, 6.4 meters, 6.40 meters, times the sine of 30. That's 30 degrees. And since the sine of 30 is 1/2, this is just half of 6.4. And half of 6.4 is, of course, 3.2. And so that means the height here is just going to be 3.2 meters. And now we have every single thing that we need to solve for the speed. Before we solve for the speed, though, and I'm just going to show this over here very quickly, before we solve for the speed, I think it's smart to just make sure you're not making any silly mistakes in the calculation. The way you make sure you're not making any silly mistakes in the calculation is to do what I said earlier. What if there was no friction? This object would have a final speed of the square root of 2g delta y. And so if we just very briefly take a moment, that's an F. If we very briefly take a moment to just calculate what would that final speed be if the object was sliding down a ramp when there was no friction, we can see whether our answer makes sense. And so 2 times 9.8 times 3.2, notice the height here is 3.2. I guess I should technically write it as 3.20 meters. When you do that, you get 62.72. And when you take the square root of that, you get 7.91959595, whatever. And so we'll call it 7.92 meters per second. That would be if there was no friction. So now that there is friction, it should make sense to everybody that the answer should be less than 7.92, and hopefully it is. We're going to use that equation here for the final velocity to confirm that. And so we have the final velocity. Let's just go ahead and rewrite that equation. The final velocity is equal to 2 times the whole thing, g delta y, minus mu times g times d times the cosine of the angle. And so all we have to do here is plug in. So we have root 2 times 9.8 meters per second squared times y, which we calculated as 3.20 meters, minus, and of course that's that first part here, so we're good with that. Then we have minus the coefficient 0.20 times g, 9.8 meters per second squared, times d, the length of the ramp was 6.40 meters, times the cosine of the angle, so that's cosine of 30 degrees, squeezing it in there. And when you do all that math, the way I do it, honestly, is I multiply these four things, then I multiply these two, and then hit minus answer, so I subtract off that, then I multiply by 2, then I take the square root, and when you do that math, you end up getting 6.4 meters per second. And it's important to realize, based on the calculation that we just did before that, this one down here, we said if the object was sliding with no friction, its speed would be 7.92. And now that we've calculated with friction, the speed would be 6.4. It actually makes sense because it's less. And that's it. Now, the obvious question here is, will you have one of these questions, a question like this on your test? It's a little too complicated. But a question similar to it definitely is fair game. So keep that in mind as we're moving along. But with that, that's it for conservation of energy and friction. And with that, that's it for today. Have a good one, everybody.